too high. Okay. So we're talking about vectors. You guys ever watched Despicable Me? Remember the bad guy? Vector, a quantity that has both magnitude and direction. So you'll never forget the definition. If you remember that movie, a boon to pre-calculus teachers everywhere, because it primes you guys to know the fundamental idea of a vector. So a vector is something that has both a magnitude, in other words, a displacement or a speed or some other magnitude-oriented aspect, and then also a direction. So it must have both of those things to be a vector. So you'll remember, that's okay, Jen. Long time ago, we used trig to solve triangles, chapter 5, part 4. You'll remember we did law of sines, law of cosines, and Heron's formula to find the area. You remember those fun days? Probably one of the most algebraically challenging things we've done, except for 7, part 4, rotating those conics. So many of you guys got that one right. Wow. First of all, those test results, when I looked at that, the clouds parted, the angels sang. You guys knocked that test out of the park. So I don't know if I either taught it great or made the test too easy, or you guys learned it great, or every one of those true at once. But in whatever happened, I'm happy about it, because that's the best results I've ever gotten on chapter 7. And given our challenging circumstances, that's quite a feat indeed on your part. So congratulations for those of you that did well. We're going to represent and operate with vectors geometrically. So this is a unique lesson in that respect. We've done algebra almost exclusively. Here we're going to work with geometry. So let me get you some geometric tools, which I have. And if you're one of the kids following along at home, hopefully you got a straight edge and a piece of string, which is all you need. If you don't have that, just watch and try to gather as much as you can from that. Let's see here. Put my homeboy Randall in charge of this. So Randall, if you don't mind. Give everybody a protractor and a compass. You may have to use some of the unopened ones. And then, so this is a protractor. This is a compass. Remind me at the end, and I'll have you take them all back up. Thank you, sir. So, real quick, some definitions. First of all, a vector, a quantity with both magnitude and direction. And vectors have an initial point and a terminal point. The initial point of a vector is where a vector starts, and it's generally an ordered pair that we call x sub 1 and y sub 1. A terminal point is where a vector ends, and it's usually x sub 2 and y sub 2. Now, that's not very helpful, is it? Don't get a lot of tactile feedback in this class. Was that the last of them?
Yeah.
They won't mind to share, I don't think. They're within 6 feet of each other anyway, so the infection ship has already sailed in their case. All right. And I explained that to Mr. Minton, and he was like, well, I guess there's nothing we can do about it. So standard position for a vector is when the initial point is at the origin. So initial point at the origin means the vector is in a standard position. As always, stop me if you get confused about something. Try to be reflective about my teaching. And the one bit of negative feedback I typically get is you go too fast. So help me out with that. Well, there's a method to my madness. It's intentional. It's hard to keep smart kids from getting bored. And one of the ways I do that is my rapid pace. So it's not an accident. But if it's too much and it leaves you with a situation that you can't understand the material, then make sure you write it down. Excuse me. Direction is the orientation of the vector. In other words, what is it pointed at? Vectors also have a magnitude, is the length of the vector. Now that length can indicate a lot of different things. Speed, force, displacement, acceleration. It's all kinds of things that can be indicated by the length of a vector. That is referred to as the vector's magnitude. in the quadrant bearing. Okay, so when we talk about direction in this class, in every case so far, we've talked about angles as being counterclockwise to the horizontal. So the horizontal, the positive x-axis is 0 degrees, right? Or 0 radians. And then we rotate counterclockwise. So that's the way we've talked about direction exclusively in this class. Now I'm going to challenge you with 2 additional ways to consider direction. And these are ways that are drawn from real-world applications because, like conics, vectors have an absolute ton of real-world applications. Airplane pilots, naval commanders, people that move ships or other things along the sky or the sea, they use vectors continuously, and they all have kind of their pet way to describe the vector's direction. So one of these is quadrant bearing. And so you're going to have a direction, north or south, then a degree, and then east or west. So what this means is 35 degrees east of south. 35 degrees east of south is how you read that. So the rightmost one comes first. 35 degrees east of south. So if you consider south as your starting point, you go 35 degrees in an eastward direction. And remember to never eat soggy waffles. To remember the points on the compass. I've got one of those for almost everything. Never eat them soggy waffles. Actually, soggy waffles are delicious because they're completely full of syrup. Syrup saturation is an important factor for me in waffle consumption. True bearing. So this one is more commonly used in aircraft applications. So true bearing says due north is 0 degrees, and we're going to come clockwise from due north. And it's going to be a 3-digit number, even if the degrees are only need 2 or 1 digit. It's always 3 digits for a true bearing. So we start at 0, and then we'll go clockwise. So 060 is 60 degrees east of north. Everything is east of north in the true bearing case. So we start at north, we go clockwise or eastward. This many degrees is called true bearing. And you'll infer it from context. As in this case, if you got a 0 in front of a 2-digit degree, you know that's a true bearing. Otherwise, they'll tell you true bearing, because if it's 135, it's a little more difficult to infer that they're talking about true bearing. But in the case of the book examples, they'll tell you in cases where it's not obvious. Parallel vectors have the same direction. Equivalent vectors have the same magnitude and direction. Opposite vectors have the same magnitude, but an inverse direction. In other words, the direction is opposite, 180 degrees different from the original. Those are called opposite vectors. And they cancel each other out. The resultant is the sum of vectors. So this term means when I add vectors together. The resultant. And there are 2 ways to find the resultant. They're called the triangle method and the parallelogram method. The only one we're going to concern ourselves with is the triangle method. As the parallelogram method is dumb. It's just doing the same work twice and calling it efficient. A little late in the day for coffee, but it's staying up watching CNN, trying to watch history play out. It's interesting because I've got 2 sides of my family that are oppositely oriented politically. And here I am in the center just eating popcorn, Michael Jackson gift, and they're like worried to death. All right, continuing here. We got a 0 vector, which means the magnitude is 0. And the components are the parts of a vector. So if any vector is going to have an x displacement and a y displacement, those will be its components. Rectangular components, we call it. So and it's written like this: lower or less than symbol is a delineator. It's not an operator. Just kind of like stands in for the parentheses, but it lets you know it's a vector instead of an ordered pair. So less than symbol, then the x component, comma, y component, and then greater than symbol. So that indicates a rectangular component form of a vector. Another quick note is, how do you write a vector? So in your book and in other textbooks, it's often bolded. In other words, if I have a vector v, which is a common variable used for a vector, it's a bolded v. That's difficult to do on your own notation. So when you're writing a vector, typically, let's see, we'll write it like this, with a little half arrow hat. So that's vector v, vector t, vector z. You guys get the idea. That little half arrow hat indicates that it's a vector quantity. Used to be a lot more commonly used than it is now. Nowadays, most of the time they use that bolded text, which is just kind of a, I don't know, less informative way to do it. Because unless you've got a real eye for thickness of font, you might overlook that. You're never going to overlook the half arrow hat. This is the way to go right here, boys and girls. Okay, so let's talk about, you're just going to talk this time, so no writing this down. Just think with me. Is this a vector or not? A hockey puck shot northwest at 60 miles per hour. Vector or scalar, Randall? Vector. Correct, because it has both a magnitude, 60 miles per hour, and a direction, northwest. Sir?
What's a scalar quantity?
So just 60 miles per hour is an example of a scalar quantity. It's one that only has magnitude, indeed, without direction. Okay, so what about this? Tennis ball served at 110 miles per hour, Anna? Correct, because there's no direction. Now, in real life, you couldn't hit a tennis ball without a direction. But as it's described here, it's not described in vector form. 110 miles per hour would be a good serve. It would be a great serve 20 years ago. Back in the 80s, that was professional speed. Nowadays, that's not. Those guys hit 140, 150, I think. Yeah, Serena Williams, I think, is around this number. So the best female players, I think, are around there. It's an amazing serve, nonetheless. State whether a sprinter running 100 meters north, vector or scalar, Maggie? Correct. No, I'm sorry. No, yes, 100 meters north, vector, correct, yes. Got myself mixed up. All right, what about this one, Luke? A tow truck pulling a car due east with a force of 100 newtons. Correct. Now, displacement does not have to occur for a vector to exist. If I push this table gently, I'm applying a force vector to it. The magnitude is not displacement. It's the newton meters of force, well, newtons of force I'm applying. So force vectors do not automatically include displacement. Let's say 100 newtons is not going to pull the car unless it's sitting on a flat frictionless surface. So he would be pulling the car but not moving it. When he pushed the gas down, suddenly displacement would occur, and this would go up. But the newtons of force are present often whether or not the object is moving. You're just not overcoming the friction with a force that's too low. All right, so let's talk about some rulers and protractors. So we want to draw an arrow diagram for V equals 10 newtons of force at 30 degrees to the horizontal. So when you see this means we're going to use the method we've always used. So this is the traditional way of determining an angle. The two new ways I've shown you we'll use as well, but this is just the traditional way when you see to the horizontal. All right, so if I come here with my protractor, you guys can just sketch a little axis. we want to go 30 degrees to the horizontal. So what I'm going to do is put a dot on the 30-degree ray. Do you see how I've done that with the compass here? I went to 30 degrees and just put a little dot on the outside of it. So that gives me a line. And now I'm going to use my straight edge. And you have a straight edge also on that protractor. So I'm going to use my straight edge and measurement to go. I said 1 inch equals 1 Newton. So on this, I need to go 10. A little bit hard to orient it properly here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, I put that dot in almost exactly the right spot. What a coincidence. It's almost like I've done this problem 1,000 times. So we'll start here and land on our terminal point, and then I can kind of clean this up and make that more obvious. I'm going to erase that point so it's more clear what's going on. So we've got here that vector V equals 10 newtons. So the way you would use Euclidean tools is you would have 10 measures of strain, inches in this case, and then you'd make an arc and you draw up to where that arc met so you draw through the point that was on the right angle to that arc. So you could use Euclidean tools for this, but so the inches being on this makes it not exactly a Euclidean tool, but whatever, it's not. This is not 500 BC, so we don't have to confine ourselves to that. All right, so that's vector V. Now let's talk about vector Z, 25 meters per second. Let's use a little different scale here. Let's use 1 inch equals 2.5 meters per second. 25 meters per second. It's pretty dang fast. Not quite bullet fast, but like a golf ball you've hit at maximum speed fast. Not me, I suck at golf, but somebody that's good. Man, my dad was the sweetest, most patient man. He was a great coach his whole life. But he took one look at my golf swing when I was a teenager and said, "That's the worst swing I've ever seen. You'll never be a golfer." So, thanks, Dad. In his defense, it is pretty bad. You can imagine looking at my body type, how flexible I am. Okay, so this time we're going to use quadrant bearing. So we're going to go 70 degrees west of south. Remember, these are read backwards, kind of. 70 degrees west of south. So I look at south and I go 70 degrees in a westward direction. Let's use our protractor to do that. So this is 270 degrees. You see, if I go 70 degrees this way, I land at 200. Stop me if that confuses anybody. 270 here, 70 degrees this way gets me to 200 degrees. Sorry.
So the west and the south is besides what quadrant you're using?
This is where you start at.
Okay.
This is the direction you travel. This is how many degrees you travel.
Okay.
So I start at the south and I go 70 degrees towards the west. So 70 degrees west of south, which winds up being 200 degrees in a traditional angle. So there's the point that's on our solution ray, and then we need a certain length. So I said we'll do 1 inch is 2.5 meters per second, meaning we need 10 inches. So let's just get it lined up here. It's pretty close. And I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2, 3, 5, 6, 7, right there. So we don't need that one anymore. clean up this a little bit. Calibration is always ever so slightly off on these. Don't need that anymore. So that's our vector z, and it is 25 meters per second. Sir.
Where to put this?
Sure. All right, so we want to start with southward. Start here. And then you see how 90 is what we start there, and then go down to 20. So just put a point right there, and that tells you where to go. And then you say, you'll have to use a different scale. So you can say 1 inch equals 10 meters per second. In that case, you go 1, 2, you go through that place. 1, 2. Yeah, this scale might not be practical on, a real inch is way too much of your paper, so you could use 1/4 of an inch is 2.5 or whatever. Good question, Grayson. Other questions? Okay, cool. So what about this true bearing? So here we got t equals 10 miles per hour. I'm going to let 1 inch equal 1 mile per hour. You should probably let, I don't know, 1/8 of an inch equal 1 mile per hour, which is a little tick mark on your ruler. First of all, the true bearing. So the way the true bearing works, this is 0. So what I could do is rotate my thing so we're 0's there. Let's see, actually. There we go. So I can rotate my compass until 0's there, and then the inner ring is the true bearing here. So we want 25 true bearings. So that starts at north and moves clockwise. And this would be a point on that ray of 25 degrees. So I have to, kind of hard to do that, but that's pretty good. So now we want to go 10 inches along that ray. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right there. And I need a vector to land on that point. Erase those points. And that is the representation of vector t. 10 miles per hour. That'd be a very fast jog or a slow sprint. Maybe a lineman sprint. Most commercial treadmills have 10 miles an hour, so it wouldn't be unusual at all for a person to be able to move at that speed. An extremely fast sprint would be like 20 miles an hour. Professional athlete sprint, maybe like 22 or 3 miles an hour. Of course, nobody could do that for a sustained period of time. It'd be a very brief thing. We're not designed for that. Humans were endurance hunters in hunter-gatherer environments. In other words, we just chased animals till they died of exhaustion, and we killed them. They still do that in Africa. The tribes of humans that still live as hunter-gatherers, they still hunt that exact way. In the Kalahari. There's a really neat movie called The Gods Must Be Crazy about a tribe of people that do that. It's got some, tribal nudity in it, but I think it's free on YouTube. I think we're squared away on those. So resultants, this is on page 484. And it's about how to add vectors together. The only way we're concerned about is this leftmost way, which is the tip to tail. In other words, I take the tail of the first vector and attach the tip of the second vector, and the terminal point of the second vector in that case is the terminal point of the resultant. So it's a geometric way to add them. You know, if I just gave you two vectors and said, figure out how to add these together, you would probably happen upon this technique. Very intuitive. Sir?
So just adding the magnitudes.
Indeed. Well, and the directions. Averaging the directions and adding the magnitudes, yes. But the x, you know, see how this has a negative y? This has a positive y? So there would be some cancellation in that adding of the magnitudes in the x and y directions respectively. But yes, that's a good approximation of what's going on here. Other questions, thoughts, comments? All right, cool. So here's about a chick that went hiking. She walks 2 kilometers west of north from her camp and then walks 2 kilometers directly east. How far and at what quadrant bearing is Shelley from her camp? So let's decide on a key here first. I'm going to go 1 inch equals 1 kilometer. And so she's going to go, actually, you know what? I'm going to go 1/2 inch equals a kilometer. No, I'm sorry. 2 inches equals a kilometer. Because I want it to be a little longer. It'll be easier for me to make my analysis in that case. So I need this to have 4 inches of magnitude because she traveled 2 kilometers. But I need to figure out where 30 degrees west of north is first. So let's put a point 30 degrees west of north. So north in this case would be 90. 30 degrees west of that would be 120 degrees, right here. So that's 30 degrees west of north. That's the direction we want to go. And then I said 1 inch, and I need to, once I use this, I need to keep it the same because I'm going to have to use it to compare some distances. That's pretty good. A little bit that way. There we go. So 4, where it says 4 is what I want to get to. This would be the terminal point. So that's Shelley's first walk here. We'll call that V sub 1. Then we're going to add V sub 2, which is 2 kilometers directly east. I don't need, you know, if you wanted to orient, you would have to use this now as the origin. It's not necessary in this case because she's traveling due east, so we know that's exactly horizontal. So I need only make my straight edge perfectly horizontal, and then come here and I'll go 4 units due east. So there's V sub 2. Which I'm calling her 2 kilometers directly east. So 2 kilometers, 30 degrees west of north, that's V sub 1. 2 kilometers directly east, that's V sub 2. And then what is the resultant? That's going to be this vector. And we want to describe that. Excuse me. So let's find its angle. like about 75 degrees from the horizontal, but they're using quadrant bearing. So if I do that, it's 20 degrees east of north. So 20 degrees east of north is the direction. And its magnitude is going to be 3.5, actually, almost exactly 4, isn't it? It's an equilateral triangle, I think. So I think she's 2 kilometers at 20 degrees east of north. Now the level of precision goes down when you're using tools like this. Algebraically, we can find it exactly, and it would probably differ a little bit from this geometric result. That's okay. These tools are designed for approximation, not for exacting measurements. In the ancient world, they would use these to do things like build the pyramids. So, I mean, you could get a pretty arbitrary level of exactness if you're willing to put the time and energy into it. We don't have the time and energy here to do it, but if you're willing to practice and really perfect the art of using these Euclidean tools, some amazing things were done with them in the ancient world, in architecture and so on. Don't worry about the parallelogram method, that's trash. Multiplying vectors by a scalar. So if I multiply a vector by a scalar, its magnitude is what's multiplied. That's it. Except in the case where it's a negative scalar, in which case its direction is also made opposite. So if I multiply a vector by a scalar, its magnitude is scaled by that factor. If it's negative, its orientation is reversed and its magnitude is then scaled. So multiplying vectors by a scalar, it's very intuitive. It works exactly the way you'd expect it to work. So let's look at an example. So this is vector A, this is vector B. We're given their geometric entities. Notice there's no numbers here. This is just the geometric entity of A and B, and we want to draw a diagram of A minus 3B. So B is going to be scaled by -3. So first of all, we can take A, and let me show you a neat way to just create a copy here. It's not perfect, is it? I'll just do it like this. So that's A. And we can pull it out like this. So we'll start with that because that's A. Now we need -3B. So once again, I'm going to copy B here. And you just write your own little A and B on there. Make up your own. It's okay. It's arbitrary anyway. Doesn't represent any real value. So there's B. So I can take out a B. I don't want B, right? I want -3B. So the first thing I need to do is change its direction because of that minus. So if I flip left, right, and this is just using the tools on here, flip up, down, it makes it backwards. So that's now -B. And I want 3 times that, so if I do it like this, then the whole thing is -3 times vector B. And if I attach those 3 things, actually I need to undo my cloner here first. If I take those 3 and go to the tip to tail with the other vector, I now have A minus 3B, purely geometric from here. So this is A, this is minus 3B. And this is A minus 3B. All right. Questions about anything? Thoughts or comments? Pretty intuitive. If you love geometry, you're probably like, wow, this is easy. If you hated geometry, you're probably like, nah, give me an algebra problem. Okay, I don't want to beat a dead horse. I think you guys are squared away on that. I think we're squared away on that. Let's see, there's one I want to do here. Here we go. Okay, so digging in the garden doesn't really look like a will, does it? It's 2020, so whatever. Will pushes a shovel into the ground with a force of 630 newtons at an angle of 70 degrees. Draw a diagram that shows the resolution of the force that Will exerts into its rectangular components. So they want us to geometrically create rectangular components, and I'll show you what that looks like. So the first thing we need to do is find this angle. So he goes at 70 degrees to the ground. But you see how the force is applied here into quadrant 3. So it's on this ray, but it's actually this angle. So that would be 250 degrees. So the force comes from 70 degrees and then down through 250 degrees like this. And vertical angles, like if this is 70, this is going to be 70, therefore that has to be 20. So 20 less than 270 is 250. So anyway, the angle to the horizontal for this is going to be 250 degrees. And 630 newtons, we just need to pick some kind of scale. I can say 1 inch equals 10 newtons of force. Pretty close there. 1, 2, 3, 4, 5, 6, and then a third. So somewhere like there. Well, calibration got me, but something like that. So that would be the terminal point. So this is the vector. Its rectangular components are going to be, let me change the color here. First of all, this is the y component. It's how far it goes downward. And then, let's see. Guess I got to go back to this first. We'll do orange this time. And this is the x component, how far it goes left to right. So those are the rectangular components. This is the y component. This is the x component. And this is hard to assess, right? It's hard for me to give you a problem like this because I don't know if you've got Euclidean tools at your house or whatever. What scale did you use? I would have to figure that out for each problem. So I'm going to show you the algebraic way to do this as well because I made a little gym kit. You remember what I did last week? Kind of like Kahoot, but you played at different times. So I made one of those for these, but you'll need to know how to find these algebraically to get all the questions right. And I very much appreciate the effort level some of you guys put into this, but you don't have to play it for hours. Just get to a point where you feel comfortable and stop. I appreciate it if you do that, and that shows me that, man, this kid really wants to learn. So I appreciate that. But, just go until you feel comfortable with the material, and that will reflect in your result. I'll be able, because I can see how many questions, how long you spent on it, and so on. And my rubric is going to be, do I feel like the kid, spent enough time to learn the material? If so, 100%. But, if you got 10 questions wrong and then quit, that's not 100%. Okay. Anyway, finding these algebraic. So what we're going to do is we're going to make a reference triangle. So we've got 630 for our hypotenuse. That's the magnitude. And then we know this angle was 20 degrees. We know this angle is 90 degrees, the rectangular component. And then as a consequence, this one is 70 degrees. So I can use a little trig. You guys remember trig, your faithful friend from chapter 5, to find these unknown sides, x and y. So first of all, to find x, I can say the cosine of 70 degrees is the adjacent over the hypotenuse. Solve this for x. And then make sure your calculator's in degree mode. Remember what a big deal that was back in the day. So 630. People have been having me do election calculations all day, so crazy stuff. What percentage does Biden need to get to the moon? 215.5. And it's in the same units, and this is newtons. Any of you guys in physics right now? You could probably attest to how anal physicists are about units. You got to have, most physics teachers, I don't know if Jeff is this way, but most physics teachers will count off half if you leave the unit off.
Yeah, he mainly does that with significant digits.
Yeah.
He's really big on that.
OMG, I hated significant digits because it was arbitrary. It's just like somebody picked. And it's not like you're adding data, you're just giving a closer approximation. Anyway, y equals, I better do the whole calculation. Don't want to skip ahead. So we'll do sine of 70 degrees equals y, the opposite over the hypotenuse, 630. And so y equals 630 times the sine of 70 degrees. Show you a neat calculator trick. You hit second and enter, it puts in what you just put in. And I can go over here and change that to sine, making it really efficient. 592 newtons. So this is our our x component and our y component. Now, these are positive. You're always going to get a positive result. I know, however, this displacement in both cases is negative because it's in Q3. So you must do a sign, S-I-G-N, analysis after the fact to determine if they're positive or negative. Okay. So the method I taught you will give you the magnitude of the component vector. It won't give you the direction. It'll be either positive or negative. In this case, both negative. So I can say this vector, we'll call it V, is negative 215.5. Move this stuff out of the way. And then negative 592. Yeah. So that's the last skill you need to be successful on that little assignment I gave you. If you go to Google Classroom, you'll see a link to this. I'll put the link up here as well in case you just, for whatever reason, you think it's more convenient to type it in. But that's the assignment. So do your best with that. If you have any problems, email me. This is the first time I've ever used this, so potential for error is pretty high. If I have a bad question in there or something, just let me know.